Well, first, let me thank Rachel and the other organizers for inviting me here. It's the first time to Santa Barbara, so it's been great. Sorry, I lost my first sentence here. That's weird. It's the jet lag. It is the most jet lagged I've been since I've been here, the third day. So let me start by something I'm not going to talk about. So that's the spirals and bars that NURCAM all of a sudden showed us, right? Many people said bars and spirals cannot exist because the disks are too hot, etc., etc. Well, there they are. Something I've been thinking about and that I'm interested in. I'm not going to talk about. I'm just showing this because I know there's probably 3 or 4 people who are also interested in that in this room, so we can chat about it. But I think it might become important for galaxy evolution and the way we think about the structural evolution of galaxies because of the torques these things can exert. So the 2 things I do want to talk about, they're strictly James Webb related. The first one is not quite first billion years. That's what I was going to say. I'm not really a first billion years kind of person, right? So keep that in mind. And the second topic, when I start looking at those galaxies, redshift 6 and above, that's exploratory for me. So I'm just going to share my first impressions there. And I know I'm talking to a room where there's people who spend a lot more time and effort thinking about how to measure galaxy sizes or redshift 10. So it's my 2 cents and a conversation starter. And I'm looking at you, Brent. I know you've been working on this very hard. So it's a conversation starter from this perspective. Okay, let me first talk about lower redshift, so cosmic noon, right? With candles, 3DHST, we basically settled the debate on what galaxy sizes are in the rest frame optical redshift 2, right? And now we can do the same in the rest frame near infrared with NURCAM. So this is what we did. The reason we could do this quite efficiently is because we used other people's hard work. So I want to acknowledge the Cosmos team for putting together the Cosmos 2020 catalog, right, which gives us redshift, stellar masses, rest frame colors, etc., and publish that catalog. And then, of course, there's Casey's beautiful Cosmos Web data, the NURCAM mosaics that we freely used as we downloaded them from the Dawn archive. So we looked at the NURCAM images targeting the galaxies that we already knew existed, redshift 1, 2, 2.5, right? And just studied their light profiles. So this plot shows you the stellar mass and redshift distribution of our sample. We chose a sample that's complete down to 10 to the 9 stellar masses, which is a high stellar mass for redshift 10, but it's a low stellar mass for this redshift range. The color coding is the singleton noise in the F277 filter. And that's just to show that there's plenty of singleton noise in essentially all of these galaxies to do a decent profile fit. Okay, what we did in terms of profile fitting is standard procedure these days, right? You have an image, you make a single component surgic profile, in this case the 2 long wavelength filters. They agree very well in this case. They're no different. 1.6 kpc, surgic index of 2, and the residual looks good. Right, so we did that for the 26,000 or thereabouts galaxies in our sample. And then the question is, what happens with the sizes compared to the optical? So this is a first redshift bin, below redshift 1 even, present day universe essentially. So the dashed lines are the rest frame optical sizes from candles, right, for the star forming galaxies. These are the rest frame near infrared sizes from Cosmos Web. So they're smaller at high mass, 10 to 11th. They're more smaller than at low mass, but the whole thing is shifted down a bit. And we see something similar for the quiescent galaxies. So these are the passive galaxies, early types, if you will. This is their median sizes in rest frame optical. They're shifted down in the rest frame infrared. Okay. Now this is of course related to mass light ratio gradients, star population gradients, maybe dust attenuation gradients. This makes sense for late time galaxies, right, which have bulges and things like that. So the question for you is, what will happen at higher redshifts, right? Now, in these 3 next redshift bins, what do you expect to happen? On the one hand, you could think, well, there's fewer old stars at high redshift, so the color gradients go away, and the sizes are more similar. Same for the coalescing galaxies. Or maybe there's more dust in the centers of galaxies at high redshift, so maybe the difference gets bigger. So, take the temperature of the room. People are thinking on their feet. What do we think? Does the difference go away? Who thinks the difference goes away? Okay. Who thinks the difference gets larger? Who thinks it stays the same?
Are you tracing the same red frame?
Yes. Okay, so those are the people that read the paper. So here we go. So at progressively higher redshifts, we basically see the same. The difference in red frame optical size and red frame near-infrared size is basically the same at all redshifts for the coalescing galaxies and for the star-forming galaxies. So in this row of panels here, there's that offset, right? You see that it's pretty flat for the coalescing galaxies. No matter the mass of the coalescing galaxy, the sizes are about 0.1, 0.15 dex smaller. Now for the star-forming galaxies, you see this mass dependence, right? The whole size mass relation is flatter for star-forming galaxies. Now this directly impacts what Andre said about the galaxy size, halo size relation, because the shape for the disks matches very nice with the shape of the stellar mass halo mass relation, but now we're making it flatter. So what are the implications? I don't quite know yet, but something is changing. But it's remarkable that at all these different redshift bins, so this is, well, from 4 gigayears ago to 11 gigayears ago, there's a constant offset, right, and the same behavior. Now,
what's the bottom panel? The offset between the JWST and the older?
Yeah, the offset between the dashed line and the solid line. So the size difference, optical and near-infrared rest frame. So these redshifts, we know it's mostly dust in the centers of massive star-forming galaxies that causes this offset. So you basically don't see the bright centers of massive star-forming galaxies. You only see the outer parts, that's the star-forming disk, right? So the galaxy looks large, but there's a dense, bright center that only turns up in NIRCam. You didn't see it in HST, yeah.
Is it really dust or just the formation happening in spiral arm?
The centers are dusty, and there's more, especially at redshift 2. In these massive galaxies, the star formation tends to be concentrated in the center. There's also a star forming disk that's extended that you see in the UV optical, but there's a lot going on in the center. There are many indications that that would be the case from ALMA, right, in these types of galaxies, so that's not entirely new. But here we see the effect on the galaxy structure. So these massive star forming galaxies, they're quite bulgy already, and you didn't quite see that in the HST images. Okay, since these offsets are pretty much constant with redshift, there's not too much that's going to change in terms of size evolution with redshift, right? So this is the rest frame near-infrared size, median size as a function of redshift. So with star-forming galaxies, you see this steady evolution with redshift, 1 plus e to the bit flatter than -1, just like in the rest frame optical. For the coalescing galaxies, we see very fast evolution in the sizes, just like we saw with HST. So it's all confirmed with the NIRCam images, right? Rapid evolution of massive coalescing galaxies. I forgot to mention the different colors are different mass bins. Yeah. One thing I forgot to point out is that this black line is the combined sample of star-forming and coalescing galaxies, and then you see something that I hadn't really realized before, namely that a 10 to the 11 solar mass galaxy is basically the same size as a 10 to the 9 and a bit galaxy. That's kind of weird, right?
When you combine everything.
Yeah, just a galaxy is a galaxy, right? It consists of stars, and this is its size. 2 orders of magnitude difference in stellar mass, and hardly any difference in effective radius.
That's the rebalancing between the quiescent and high mass and star forming low mass.
Yes, But I feel like sometimes we go a bit overboard in separating two types of galaxies because it's really a continuum of profile shapes and mass distributions. Anyways, I'm lingering on this topic too long. So what we have learned from this analysis is that when we compare Western, infrared, and optical, that the sizes are generally smaller by about 30%. For star-forming galaxies, there's a mass dependence, so the whole size-mass relation is flatter in the Western infrared than in the Western optical. But the pace of size evolution with redshift is essentially the same as in the optical. Now the next step is, of course, come from the optical to the infrared is one big step towards understanding the stellar mass profiles of these galaxies, but it's also in the infrared you have mass-light ratio variations. So the next step is obviously, and many people are working on that, is to get the stellar mass profiles and get the sizes of those profiles and then make these plots again. I think they're going to look like this. Okay. So the other topic is the redshift larger than 6 galaxies. Now what I'm going to do is very simple and basic. Thank you. So I'll have to speed up a little bit. There's been a number of papers discussing the small sizes of the high redshift galaxies. Andre talked about that from the theoretical perspective. So this is the regime I'm going to talk about. Right? Here's a plot from Ormerod and Consolis. Some galaxies are really small, close to 0 on the scale. Others are a kiloparsec. So just in preparation of this conference, I decided to look at, to see what these things look like out of curiosity and to have a conversation with the real first billion years kind of folks, right? So this is the sample I looked at. I took the Morishita 24 dropout sample. I was stunned to see a dense Stark sample of more than 100 redshift 9 dropouts, so clearly we're behind the curve here. But this is the sample. In absolute UV magnitude, stellar mass, just to give an idea of where we are, and as a function of redshift. Now the larger points have singleton noise larger than 20 in F150, smaller points less than that. Singleton noise is 20 is sort of my line where I say, now I can measure a galaxy size, and now I cannot. Of course, if you push harder, you can do more, but that's what I learned from analyzing the candles data. So what we're up against is the challenge of, so this is what HST told us the galaxy sizes are more or less at this redshift range, right? But this is the HST PSF. It's larger than the galaxies. Now, with F150, we have a shot. This is the PSF size, this is the pixel size, right? So we can resolve this now and push down towards this 100 parsec regime. But that's a challenge we're up against. So here are my galaxy sizes, fit in the same way as I did the lower redshift sizes. That's a single searching profile to the mosaic, right? And I know that in JADES there's much more advanced machinery to build from the individual frames, the light profiles, forward model, etc. But this is what happens when I use my standard methodology. Here the sizes as a function of redshift. And you see, well, they're about kiloparsec, 300 parsecs. These are the mean sizes with the statistical uncertainties. Maybe there's redshift evolution, maybe there's not. Now, well, what do these galaxies actually look like, right? So let's take a look at these two largest bright galaxies. They look elongated and clumpy. Nothing new. People have seen that, right? So we can easily resolve that size. Now, let's also look at the 300 parsec galaxies, basically the same size as the PSF. Are we looking at something real? Well, I think so. It's a bit, these are not point sources. There's fuzz around here, right? So it's important that these profile fits survive the by eye test, right? You can have very advanced machinery, but if it doesn't match with what your eye tells you, these things are resolved. They're not point sources, so a size of 300 parsec, I can believe that. It's fine. I warned you, it's very simple what I'm doing here.
Can we do better than our eye or statistics?
Well, that's what these fits are, right? I did the fits, and then I look at the image to see if it's a point source or not. Okay. Now, in the Morishita paper, they also published sizes, so I'll blink back and forth. They're smaller, right? And that must be a difference in the PSF model. So if I consider that an uncertainty, and I fold that into the statistical uncertainty, I can draw error bars like this for the size evolution, and it's just not clear if there is size evolution or if it's consistent with both, right? Okay, the very last thing I wanted to show is these two largest galaxies, they're elongated, right? And that's part of a larger trend. Here's the size, here's this projected axis ratio. The large ones are elongated, the small ones are not. This is a trend we know at redshift 2, but it's subtly different. These are the redshift 2 galaxies of the same mass. There's not much of a correlation here, but they're on average much flatter than these guys. Right? Now, this is the topic of the next talk. What do these shape distributions mean? I mean, that's Viraj's famous bananas galaxies, right? The redshift 2, they're bananas. And this is suggestive that at very high redshift, there's fewer bananas. And that there's more actually round galaxies, compact things. Again, very simple. Okay, so what we've learned is that I think we can agree that the galaxies are small, but every galaxy that I've looked at is resolved. There's nothing below the PSF. Now, there have been other measured sizes way below the PSF. It's a different sample, right? But well, it's obvious to me that with these, at least in the short wavelength channel, we can measure these sizes robustly. At the long wavelength channel, you need to use advanced machinery because the PSF is a factor 2 larger. It's much more challenging. Okay, thank you for your attention.
Start with Dale. Can you just grab that mic?
Great work, Arjen, as always. I'm curious about the sources at redshift 1, 2 that are getting smaller with a single Cerseic fit. Is there any possibility that there's an unresolved nuclear component that is showing up as you go out to longer wavelengths that might be driving the effective radius down? Is there any sign of that in the residuals?
In some galaxies, there could be. Now, many of these massive galaxies are not well fit with a single Cerseic profile to begin with, but I blame the stellar bulge rather than a point source. But the single Cerseic profile fit still gives you a good idea of the half-light radius of this galaxy. It's not driven by a point source. There could be a few, right, that they're hiding in our sample. But the referee also asked, so what about AGNs? So we looked at all the X-ray AGN, and they didn't even have different sizes on average. We threw them out, we kept them in, it didn't matter.
Thanks.
Crystal?
I'm just kind of curious, in this higher redshift sample, right, you're now looking at the rest UV, at least the near UV. And I mean, in some of these examples, right, you've got like a couple clumps, yep, maybe 2 clumps of roughly the same luminosity. So like, what is the Cerseic fit doing in those cases? Like on the right, is it picking one of the clumps as the center, or is it picking someplace between the two as the center?
So in this,
suggesting that in a longer wavelength image, we would see something between the clumps, or do you have any clue of physically, right?
Yeah, no, it's true. Like these single Cerseic profile fits are designed to, model galactic disks or an elliptical, right? And that's not what we're doing here. This is just to get an idea of the spatial extent of whatever we're looking at, and depending on how you tweak your segmentation parameters, that thing splits up into 2 small things or 1 big thing. In this case, the stellar mass UV luminosity I showed is from the combined object, and so is the profile fit. So the center is somewhere in the middle. It's in this elongated thing. That's why the result axis ratio is small. And I'm not thinking that's an inclined disk, obviously. But it's again, the summary statistic that the single Cerseic profile gives you is decent. This is the half-light radius of whatever that is, right? It's not 100 parsecs, it's a kiloparsec, as opposed to these other things. But the scatter size is quite large here. So one way to think about it is that galaxies that are a kiloparsec or larger are a collection of clumps that were identified as a single object. And down there you have things that are a single clump.
But I'm kind of worried that adding one more clump to this stuff on the side.
Right. No, that's true. So I have to think about you have to in these cases, visually check what's happening. Are you fitting what you think you're fitting? What does it tell you? But at some point, it's semantics. Is that one galaxy or is it a merging galaxy? Is it much more massive gas disk with 3 star-forming clumps? I'm completely agnostic at this point. Is it just the detection software decided this is one single object, I'm fitting the light profile, and this is my summary statistic of the spatial extent and interpretation? That's next.
Can the next speaker come up and we'll do one more? Brant, you had your hand up first.
In the next slide, you say, oh, well, you don't have to show it. You just say that the objects that are elongated are not disks. Maybe it's the slide after this one. But you know, I'm wondering how stringent of a constraint you can place on a mixture of objects that are disks and clumpy things that are elongated.
So if you have an access ratio distribution like this, and there are all disks, suppose that's one extreme, right? Then you cannot explain this correlation with size.
But with a mixture.
With a mixture you can. So, but then it's kind of suspicious that the phase on disks are missing. That could have to do with the data as well, on surface brightness and stuff. There could be a mixture, but this is such a, I think we're really looking at elongated chain-like galaxies, right, in this case. But this is really the train of the next talk, so let's move on.
Awesome. Let's thank Arjen again.